Hey everybody! In this video, we are going to talk about a concept known as solubility. Solubility is just how well the solute dissolves into the solvent. Now, the units for solubility include grams of solute over 100 grams of water, or in other words, how many grams of solute can dissolve in 100 grams of water. Now, we could also do grams of solute for every 100 mLs of solution. We could also do, especially for very dilute solutions, milligrams of solute per liter of solution. We also have ppm, parts per million, and ppb, parts per billion. And note that the list goes on, and these are just the most common ones. Now, before we start this video and go into the concepts behind solubility, you should know, or you can review, concepts behind bond enthalpy, concepts behind video 8.1, which was a video that introduced us to the idea of solubility and concentration, and you should also review intermolecular forces, and all this will prepare you for this video. So, when we talked about like dissolves like in video 7.6, that holds true due to the ideas behind intermolecular forces. So we will do one example to explain why like dissolves like. So H2O and NH3 are both polar compounds. They both have hydrogen bonding, and they both have LDF, of course. And since they're polar, they both will also have dipole-dipole forces. Now, these two compounds have the same intermolecular forces, so why do they dissolve each other? And before we continue, you can see that the solubility in water for NH3 is 90 grams of NH3 per 100 grams of water at 0 degrees Celsius. Now that is a lot, and that just shows how NH3 is highly soluble in water. Now, why is this so? So, I'm going to explain this in the format of a little story, and let's talk about the story that I made up. So, we know that H2O has H bonding and many other intermolecular forces between them. So there's also dipole-dipole and LDF, but we are going to focus on H bonding since that is the major LDF, since it's the strongest out of the three. Now, we have NH3 gas. Now, unlike the liquid water, which has really apparent LDFs, the NH3 gas has essentially no intermolecular forces with other NH3 molecules, since they are so spread apart as gases, and I wrote as twice, so let's delete one as. So we will pretend that there are no intermolecular forces between adjacent NH3s, even though there might be, but we are not going to consider that to simplify our model. Now, NH3 here says, "Hi, can I form bonds with you, H2O?" And why does it want to form bonds? Well, forming bonds will let the NH3 connect to the H2O, and by connecting with the H2O, NH3 can dissolve. So essentially dissolving is forming bonds with the solvent and, being dissolved. So H2O has a response to this. H2O says, "Sure thing. Although we are breaking the strong H bonds between H2Os, which takes a lot of energy, so these green bonds are the H bonds that the H2Os have to break, the formation of an H2O NH3 H bond, which is strong as well." And how does that look like? Well, this is an H2O NH3 H bond, as shown here in green. So the formation of this bond, and remember, this bond is pretty strong as well, since, it's a hydrogen bond, and since it is strong, it will release a lot of energy upon formation. Now, H2O says that we are getting most, if not all, or even more, energy back after using it to break the H bonds between the H2Os, so why don't we bond? And note that we didn't consider any of the other IMFs involved, so maybe by interacting with NH3, the H2Os could actually be releasing more energy overall than they used, and if this happens, it's an exothermic reaction, and it's beneficial. Now, you might be wondering, why would breaking bonds here and forming them here be beneficial if it's exothermic? Well, exothermic reactions are usually spontaneous, and another word for spontaneous means that the reactions work and go forward. And exothermic reactions are spontaneous because they cause the products to be lower in energy than the reactants, because that's what exothermic means. It means that the compound loses energy and releases that energy, and the resulting stuff has less energy than it did before. So because the products are lower in energy, they are typically more stable. So reactions that are spontaneous tend to be exothermic because they produce stable products. Now, this doesn't mean that they're always spontaneous, because there's another factor called entropy that we will talk about, and entropy is another factor that we consider in spontaneity. So since the breaking and forming of intermolecular forces is favorable because it is in general exothermic, then NH3, ammonia, will be able to dissolve in water, H2O. Now, in the final image, as you can see over here, the H2O does some hydrogen bonding as well as some other bonding that is not shown in the image, and it ends up having to break its hydrogen bonds and the other intermolecular forces. So, this H2O is kind of sad because it lost its H bonding, but not to worry, because I'm sure that out there in the distance there might be another NH3 molecule waiting to form a hydrogen bond with that water. So NH3 can dissolve very well in water, and again, this is because like dissolves like, and the reason like dissolves like is because the two compounds have similar intermolecular forces. Now let's talk about why unlike things do not dissolve other unlike things. So in this example, we will take a look at water mixing with C5H12, a nonpolar molecule called pentane. So as we might know, H2O has London dispersion forces, dipole-dipole forces, and hydrogen bonding. Meanwhile, pentane, which has a Lewis structure that looks like this, where we don't include the H's since we know that the CH bonds are essentially nonpolar anyways, and in addition, the bond dipoles cancel out. So for this diagram, we can see that C5H12 will be essentially nonpolar, so C5H12 will only have LDF forces between other C5H12. So for example, these two C5H12s might have some LDF going on because perhaps this could be partially negative and this side could be partially positive, and that would form an LDF. Now, let's do a little bit of storytelling in order to explain why unlike things will not dissolve in other things that are unlike the first thing that I said. So, I know that was confusing, but basically, two things that are unlike will not typically dissolve each other. So, let's figure out why. So, the pentane might ask the water molecules, hey, can we form bonds with you and dissolve in you, water? The energy to break LDF interactions between pentane molecules is not that much, so don't worry about the energy cost trying to break these LDFs. Now, what does water say? Well, water will say something like this. No way, it takes so much energy for us to break our H bonds, and we would just be forming London dispersion interactions with you, which is pentane. And the reason why H2O and pentane can do LDF is because both of them have capabilities of doing LDF, since all covalent compounds or molecules can do LDF. And these LDFs are weak, so forming these doesn't release that much energy. We don't get our energy back because it takes more energy for us to break the H bonds then is released when we form LDF interactions with U-pentane, so the reaction is overall endothermic. And endothermic reactions are the opposite of exothermic reactions, and because it is the opposite, then endothermic reactions are typically, but not always, non-spontaneous, since it increases the energy from reactant to product, and this produces less stable product since the product has higher energy than before. And on top of that, we have to spend more energy overall in the reaction process to break your LDFs, so we use up energy for that too. So these are the reasons why we won't let you bond with us. So there's no way that we, the water molecules, are going to let the pentane molecules dissolve in us, and the H2O will decide to keep the H bonds, since it's better to keep it than to break it and form bonds that are a lot weaker, because that doesn't release that much energy. And remember, you want the overall reaction to be exothermic for it to be spontaneous and for it to work. And because this reaction is overall endothermic, it probably won't happen. So the end result is the same as above. No dissolving occurs because pentane failed to convince H2O that it was worthy of dissolving in it. So because of that, the solubility of pentane in water at 20 degrees Celsius is only 40 milligrams per liter, and this is very, very little, so it's definitely not very soluble. So that's the end of our storytelling, and I hope you understood why like dissolves like, and why different things don't like to dissolve in each other. So there are many other instances, but in this case, we are just going to go over 2 instances for covalent compounds. Now, let's move on to the next topic. We are going to talk about something called a solubility curve. So let me write that. I'm going to abbreviate solubility for SOL and curve. So you see in this image, there are a bunch of curves. These are solubility curves, and they tell you the solubility of a compound in water as you increase the temperature. So in this diagram, how are we going to read the solubilities? Well, in this diagram, when we read solubility, we are certain about the tens place, and this is because we see that it's going to be 10 and 20, and a point that's between that. We know that it's going to be greater than 10 but less than 20. So we are sure that the tens place is going to be 1. Now, since we can go 1 sig fig past when we do measurements, such as looking at a graph or maybe looking at the measurement on your ruler. So in this case, since we are sure about the tens place, we can go 1 past that and we can estimate the ones place. So, for example, let's find the solubility of calcium chloride on this graph at 20 degrees Celsius. So at 20 degrees Celsius, the calcium chloride solubility curve is over here, and it's right about there. So we are sure that it is between 70 and 80, so we are sure that the tens place is going to be 7. But we're not really sure about the ones place. This would be just guessing, because there are no marks to tell us the ones place. But remember, we can go 1 past what we're sure of. So we're sure of 7, but we're not sure about the next one. So we could go 1 past, that's fine. So I'm going to guess that it's going to be 76. And this is the maximum number of sig figs you can have when reading this chart. So now let's read the chart. The first question states to find the solubility of potassium chlorate at 70 degrees Celsius. So let me erase all the marks and let's read this graph. At 70 degrees Celsius, we see that the KClO3 solubility curve hits about 30. So I'm going to say with certainty that it's going to be at least 3. But I don't know what the ones place is going to be, but since it looks like it hits like exactly at 30, then I'm just going to say that the ones place is going to be a 0. So we have to put a decimal place there in order to identify this number as having 2 sig figs and not 1, because if there was no decimal place here, you would say that there's only 1 sig fig, but since it's there, there are 2 sig figs. So the solubility is going to be 30 grams of KClO3 for every 100 grams of water. Since if you look on the y-axis, that's what the units are, grams of salt and 100 grams of water. Now, let's talk about supersaturation by looking at this problem. If we saturate 200 grams of water with KClO3 at 70 degrees Celsius, and then cool the solution down to 20 degrees Celsius, the solution will become supersaturated, as mentioned in the previous video. But if you throw a KClO3 crystal into the supersaturated solution, or scratch the container, and since the supersaturated solution is unstable as it has too much solute in it than allowed normally, then the excess solute will crystallize out and precipitate. Now, if this happens, how much KClO3 will crystallize out of the solution? So notice that in this question, I'm teaching you how things supersaturate, and I'm making you do a math problem at the same time. So I killed two birds with one stone. So we need to find out how much solute can dissolve in 200 grams of water at 70 degrees Celsius. Well, we know that at 70 degrees Celsius, 100 grams of water can dissolve 30 grams of KClO3. So, before we continue, you must remember that saturation means that you are putting so much solute that you are making it so that it reaches the maximum amount of solute allowed, and that's the solubility. So the solubility is 30 grams for every 100 grams of water. So if you saturate something, then you're going to make it so that there's going to be the maximum amount of solute, or in other words, it's going to hit the solubility limit. So in this case, if we're going to saturate 200 grams of water, we are going to make sure that the concentration of KClO3 is the maximum amount that can dissolve, and this number, the solubility, tells us exactly that. So we can do some math, and we see that 200 grams of water times 30 grams of KClO3 over 100 grams of water, and note that we have a decimal place there, and note that the grams of water cancel out, and we're left with 60 grams of KClO3, and that's the maximum amount that can dissolve in 200 grams of water, and this is called a saturated solution. So again, in a saturated solution, the concentration is equal to the solubility at that temperature. Now, we have to talk about one more thing, and that's that this number, 100 grams of water, is an exact number, because we are assuming that exactly 100 grams of water is there, and we know for sure that 30 grams of KClO3 dissolves in exactly 100 grams of water. So this unit over here is an exact number, because we are not measuring that, because if you measure something, it's not going to be exact anymore, because anything you measure is bound to have some error. But the measurement of the amount of salt that can dissolve will have a number of sig figs, since it's going to be inaccurate at some point. So that's why this grams of salt is going to have sig figs, while the grams of water, the 100 grams of water, is going to be an exact number, which will have an infinite amount of sig figs. Now we have to decrease the temperature to 20 degrees, and at 20 degrees, the solubility, according to the chart for KClO3, is going to be about 7 grams of KClO3 per 100 grams of water. So now the question is, how much KClO3 can be dissolved in 200 grams of water at 20 degrees Celsius? So we know that we still have our 200 grams of water. So we need to find out how much KClO3 is supposed to be in the solution, or in a saturated solution at 20 degrees Celsius. So 200 grams of water times 7 grams of KClO3 per 100 grams of water, which is the solubility for a solution of KClO3. Now we calculate that we will have a total of 14 grams of KClO3, assuming that we saturate the solution. So the solution is supposed to have a maximum amount of 14 grams of KClO3, and it will have 14 grams of KClO3 in a saturated solution, but as we just calculated before, it actually has 60 grams of KClO3, because remember, this is the amount we dissolved in order to create a saturated solution at 70 degrees Celsius. So now it's still there, and the maximum solubility now states that we can dissolve at most 14 grams. So we have to find out how much will crystallize. So 60 grams, which is in the solution, minus how much there is supposed to be in the solution, will give us the amount that crystallizes out inevitably after a disturbance such as adding a salt crystal. Now notice how sig figs can hurt sometimes. So here we had 7 grams, and our answer will have 1 sig fig, and when we're subtracting, we have to keep track of sig figs, and notice that the answer has to be in the tens place. So I had to round 46 to 50 grams, and thus 50 grams, about 50 grams of KCl will precipitate. So sig figs do hurt. Now that we learned about precipitation and the idea of supersaturation, let's talk about the science behind dissolving salts in water. Now, not all salts dissolve equally. Now, before we get to the formula, we have to talk about a few things. Dissolving salts involves breaking the hydrogen bonds between water and the other IMFs, of course, because the hydrogen bonding, it's not the only IMF there is. And it involves the breaking of the ionic bonds between ions. This process is endothermic overall and takes energy since you are breaking bonds. So you gotta do 2 things. You gotta break the IMFs between the water, and you gotta break the ionic bonds between the ions in order to get separate water molecules and separated ions. Now, the source of energy release comes from the ion dipole forces forming between water and the ions once each of them break their individual bonds that keep them from each other. So this releases a ton of energy. Now, the delta H of flat, if you remember, is the enthalpy change when 1 mole of salt forms from the gaseous ions. And when this happens, the ionic bonds form, because when the gaseous ions come together, they will form ionic bonds, and you will get the salt. But since we are looking to do the opposite, or in other words, break 1 mole of salt into gaseous ions, or break the ionic bonds, then the delta H of flat is negated in our scenario to match the fact that the ionic bonds are breaking here and not forming. So that explains why the delta H of flat is negated. Now, the delta H of hydration is the energy change when 1 mole of dissolved ions is formed from 1 mole of gaseous ions. Whoa, gaseous ions? Well, when gaseous ions dissolve in water, it forms ion dipole bonds, and this releases energy. And in addition, it involves also breaking the IMFs between the waters, and that is endothermic. But this happens at the same time as the ion dipole bonds form. So, since ion dipole forces are stronger than hydrogen bonds, the process is overall exothermic. Now, this is confusing. I can see that happening. So let's draw an energy diagram, and let's apply some Hess's law to demonstrate this idea. So at the top with the highest energy are the gaseous ions, and in the middle are going to be the solid form of sodium chloride. And at the bottom will be our dissolved ions. So as you can see, the delta H of solution, or the change in enthalpy when we dissolve a solid and turn it into its ions in water, this thing is going to be exothermic, since the product is losing energy overall, since the energy is going down as shown here. So this is an example of an exothermic reaction for the delta H of solution. So let's talk about how this diagram works. So the delta H of flat, as we know, is when the gaseous ions turn into the solid. The delta H of hydration is when the gaseous ions turn into the aqueous components, and you see that these 2 arrows, well, the delta H of flat arrow and the delta H of solution arrow, both add up to equal the delta H of hydration arrow. So we can conclude that the delta H of flat plus the delta H of solution will equal the delta H of hydration. So the delta H of lat will always be negative, the delta H of hydration will always be negative, and if you want to know why, just read the explanation above and read it really carefully. And the delta H of solution can either be positive or negative. So we can rearrange this equation by subtracting delta H of lat from both sides, and we get that the delta H of solution is equal to the delta H of hydration minus the delta H of lat, based on our definitions. So if the delta H of solution is positive, then the reaction will typically be non-spontaneous, and it will typically be insoluble. So I don't know why I wrote soluble, it's insoluble. Now, if the delta H of solution is negative, then this means that the reaction is usually spontaneous, and that means that dissolving will become soluble. So, let's talk about how these breaking and forming bonds are related to these delta H's. So the breaking of the hydrogen bonds, as well as the other IMFs, as well as the formation of the ion dipole forces, are all part of the delta H of hydration. And because forming ion dipole forces will release more energy than is needed to break the hydrogen bonds, then the delta H of hydration is always going to be negative. Now, the breaking of ionic bonds, which is also an endothermic process, is related to the delta H of lat. And all these processes combined will get us the delta H of solution, which will tell us if something will dissolve or not. So that's a fun explanation, and now let's move on. So, when dissolving a solid or liquid into a liquid, it is usually endothermic, since a solid, and sometimes a liquid, needs to gain energy to become solution molecules. Because if you think about it, solution molecules, we can pretend that the solution molecules are ions, for example, and these ions move around freely in water and have a lot of energy, far more energy than if they were stuck as a solid, or maybe sometimes a liquid. So solid plus liquid becomes solution, and the delta H of solution is typically positive, and we can rewrite this and say that the solid plus liquid plus heat, since it's endothermic and we gotta add heat to make it happen, will become our solution. So you will learn this in equilibrium, but adding heat shifts this endothermic reaction to the right because there's too much heat on the left. Therefore, increasing the temperature will shift equilibrium to the right and increase the amount of solution. This increases the solubility. Therefore, in general, increasing the temperature will increase the solubility of solids and liquids. So conversely, decreasing temperature usually decreases the solubility of salts. Now, this is not a perfect answer, because there's also another factor called entropy that explains solubility, and that one is honestly a better definition. But for now, let's just stick to this definition that I gave because it's accurate to a certain extent. Now, if we dissolve a gas into a liquid, it is usually exothermic because the gas needed to lose energy before becoming solution molecules, which are like liquids. Because, if you go from a gas to a liquid, that is losing energy. So in the same way, going to a solution will make it lose energy. So since it's exothermic, the heat will be released on the right side as a product. So gas plus liquid becomes solution plus heat. And because of this, increasing temperature shifts the reaction to the right. And this does not favor the solution, because if you increase temperature, it increases heat, and there's too much heat on the right side, it wants to go to the left, which is bad because that's not where the solution is. So in general, increasing T decreases the solubility of a gas. Conversely, decreasing T generally increases the solubility of gases. Now we can kind of prove to ourselves that increasing the temperature increases the solubility of solids like salts by looking at this diagram. So in this diagram, as you increase T, the solubility curves steadily rise for 90% of the salts, maybe except for this one, but that's just, an outlier. So this is just a proof to show that increasing temperature increases the solubility of solids. Now that's all for this video. Have a nice day.